Good morning.
Hello, good morning, sir.
Good morning. Can you hear me? Hello. Good morning.
Hello, good morning, sir.
Yes, can you hear me?
Yes, yes.
Okay, so we can start. Okay.
Okay.
Yes, we can start.
Hello, good morning, all of you. So, can you see my screen, PowerPoint screen? Is it visible?
Yes, sir.
Okay. And can you see the change in slides?
Yes, sir.
So,
Sure. Yeah, okay. So we can start now. So in the last session, we covered the different gear ratio selection strategies and like how to select the maximum gear ratio for a transmission and minimum gear ratio and how to select the intermediate gear ratio. And then we had started off with an activity. Uh, we were actually trying to fill up this table for Tata Nixon. So for different models. So anyone actually has gone like went ahead and have you picked up all the specifications and for filling up this table? Anyone has any things to add to this?
There was no gradability data available for petrol and diesel engine options.
Yeah, that may be possible because generally they don't report gradability for these variants. So yeah, anyway, basically, so the purpose was to uh, understand like what are the differences in the different models. So and like, considering the different prime movers that are used. So like petrol is like 1.2 liter engine and for the diesel it's 1.5 liter. Uh, so the rated power of the petrol engine is actually uh, more than that of a diesel, but the torque that we get from the diesel engine is much more. Uh, so in the acceleration performance, so someone told me it's like 12.73 to accelerate from 0 to 100 kilometers per hour. Uh, so it's more than like better than the petrol variant. So that's apparent in that like better torque characteristics lead to better acceleration performance. Whereas in the EV, it's actually further uh, better than the petrol and diesel variants. So it's only 9.14 seconds to accelerate from 0 to 100 kilometers per hour. So that is because of the full maximum torque of 245 Newton meters being available at zero speed as well. when the vehicle can quickly accelerate. And one remarkable thing to note is that petrol and diesel models, they have a six-speed transmission, whereas the EV has just one speed, single gear ratio for the entire speed range. So that was the one remarkable thing to note. So we can, so when we design a transmission, we will try to look at the performance as well as mileage. Like we want to get very good acceleration performance, and we also want to get very good mileage or range. So how much distance that the vehicle can travel over full battery charge. So then uh, to be able to achieve like all the objectives, uh, then we might need to consider multi-speed transmissions with petrol and diesel vehicles. But so with the electric vehicle, they just used single speed. So so it may be possible or may not be possible to achieve all the objectives, but uh, considering the factors of the loss in motor efficiency, if we operate, considering uh, the loss in efficiency if the motor operating point is away from its most optimum zone, that is not so significant as an IC engine. So then we can actually have make a compromise over there, and for simplicity, we can actually just limit it to a single speed transmission. So it may be a compromise like between either. So like if we want to get very good range, then we may actually compromise. We may design uh, the gear ratios such that we get like the best mileage, but we may not get the best acceleration performance. Or similarly, if we our objective may be like the acceleration performance, then we may have to sacrifice somewhat on the mileage or so. Uh, so then we actually had started this activity last time. So, so we actually uh, because we do not have any data available, we tried this activity was to let us see try to see whether we can actually design a four-speed transmission, have gear ratios calculated, the maximum and minimum gear ratio, whatever based on whatever we had learned, how to calculate the maximum gear ratio and minimum gear ratio, assuming the motor some motor maximum RPM like 10,000. So so anyone was able to calculate further what they got. So someone at the end of the session told that this they got this gear ratio of 6.38. So anyone has any results to share on this? So who I think who was the one who shared that the maximum gear minimum gear ratio was 6.38.
Yes, sir, I got that answer.
Okay. Yeah, so were you able to calculate the maximum gear ratio as well?
Not yet, sir.
Okay, okay, fine. So, I mean, anyone else tried this activity, calculating these gear ratios? So, at least I think one person has tried. So, Kshitij, right?
Yes, sir.
So can you tell us like how what was your approach? What you did to get like whatever ratio that you got?
For the minimum gear ratio, so we had that formula 3.6 pi by 30 into N max R dynamic by V max.
Right.
So we assumed N max to be 10,000.
Okay.
V max also I think was available from the table,
Yeah.
and R dynamic. So for Nexon EV, I think 16-inch tires are there. So I assumed the rim size to be the tire size for the moment and assumed 16-inch radius tires.
Okay. Yeah, but that okay, fine. Okay.
Yeah, and
Okay. So then you at like for so the radius is 16 inch for you. So like 16 inch by 2. So 8 inch radius, right? 8 inch is your radius, right?
16 inch is the radius, I think.
Ah, okay, fine. So oh, your radius itself is 16.
Yeah.
Okay. Okay, fine. Sure. So you got this as 6.38. So fine. Now, so with your whatever tire radius assumption, so can you try to calculate what is the maximum gear ratio that you get? So, so if like this is the left hand side equation is for the gradability thing. So, uh, so let me simplify that. Like so, this term you can actually neglect. So like this part, uh, this part you can just neglect. And this is the maximum torque. So this product of I, this is the overall gear ratio. I let us say this the powertrain efficiency. You can assume it maybe 90% or something like that. Or then this is the tire dynamic radius. Uh, this is the maximum torque that is available from the motor. Uh, so with that, maybe in the next, I mean, in the 5 minutes or so, like can we just quickly calculate what would you get as the gear ratio?
Yes, sir.
Okay.
Sir, I want to make a correction. So I think you were right that R16 has 8-inch radius. So I have assumed 8-inch value
Okay.
for that calculation.
Okay. 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 Fine. So that actually becomes quite small. So anyway, so then I'll just try to write the simplified equation here. Uh, so are you able to see the match type screen or
Yes, sir.
okay, fine. Yeah. So I'm actually just trying to simplify this equation. So I have simplified this equation so you can like you have like a direct expression now for the overall gear ratio. So if you can just substitute in this equation and tell me what value do you get?
Assuming smooth concrete road, so it comes out to be around 11.989, so 12.
11. Okay. 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 Oh, sorry. You told 12, right?
Yes.
Okay. Fine. Sure. Okay. Then so what is the value of alpha that you considered for this?
Uh, since the gradability is 0.34, so 10 alpha is 0.34, so I assume 88.31 degrees.
Okay.
Uh, just a second.
88.3.
Yeah, sounds something is wrong. I'll just recheck it.
Yeah. So it should be actually so tan 45 is 1. So it should be something less than 45, right?
The gradability was 34%, right?
Yes, yes.
Yes, so it is 18. By mistake, I wrote 88. So I'll
Okay.
just make that correction.
All right. All right. So like after you are done, so I'll also share whatever like I tried. So then we can compare notes and then we'll see probably some interesting observation.
I have assumed the efficiency to be 95%, but using that, the gear ratio then again comes out to be 3.97, so just close to the minimum.
Yeah, so let me just write it down. So you get what?
3.97. I'm not sure if this
3.97 as the
is,
maximum gear ratio.
yeah, I think it
Right?
is something is wrong, but I'm not sure.
No, we'll see. Yeah, so you got 3.97, right? Sure. So
Yes,
hold
sir.
on for the to that. Like you can just like in the meanwhile you can just check your calculation once. Like but yeah. So we'll hold on to this value. So I'll also share my solution now. So the motor has a maximum torque of 245 Newton meter, and it has a power of let us say 90 like 129 PS. So PS. So anyone knows what is PS? That is a like unit of power for sure. But you know what is anyone aware what is PS? it's basically metric horsepower. So it's similar to that British horsepower. It's another convention to use this unit in automobile industry. So it translates to about 94.9. So it's about 95 kilowatt, you can say. And the maximum motor speed, we assumed it to 10,000 RPM. Now, so now if we have to, like, based on our assumptions and whatever specs that we have, if we can actually try to construct the motor torque versus speed curve, right? So then we have this, we'll draw a horizontal line of 245 Newton meter. So somewhere something like this. And now another data point that we have is this maximum power. So if we want to represent this maximum power in this is torque versus let us say vehicle speed, or like torque versus omega, like forget vehicle speed, so we'll just motor RPM, let us say. So with torque versus motor speed, so it will be a hyperbola, right? So this corresponds to 95 kilowatt. So now, if we note this intersection point, so this at this point, the maximum torque is available as well as the maximum power is also available. So then this is called as the base speed. So we can find out what is the base speed. So corresponding to basically just if we do torque into omega, it is equal to, let us say, 95 kilowatt. So we know what is the torque and we know what is the power. So then we can get the base speed value. And maximum motor RPM we have like assumed it to be 10,000. So can someone quickly just tell me what is the base speed that we get? Like if we assume this way, so it's 95,000 divided by 245 in radian per second, and in RPM it will be this whole thing multiplied by 60 by 2 pi. So what will be the RPM, motor RPM?
387.7
In radian per second.
in RPM.
Okay, are you sure?
In radian per second, I guess, yeah.
Yeah, so roughly, so it some 387, right? So it will be around 3,900 or something in RPM. So roughly, uh, twice or at least twice or thrice of that. Generally, we will assume that motor maximum speed. So let us say we have assumed 10,000, and we'll proceed with that. Now, gross vehicle weight, I assumed that's like 100 kg per person, like, considering uh, 70 kg, like 70 kg per person and plus some additional payload. So I just assume like 1400 is the curb weight, and 400 kgs I've assumed like additional, like, cargo plus uh, passengers. So that I have assumed as 1800 as the gross weight. So, Kshiti, what was the gross weight you have assumed?
So initially in the table it was written gross weight, so I assume 1400 as it is.
Okay, so you just assumed 1400. Okay, fine, no problem. Uh, then I have assumed this rolling resistance coefficient as 0.01, and the value of alpha, basically the road inclination for a gradability of 34%, uh, we get 0.3277 radian. So tan inverse of that, so that is around 18 degrees. So frontal area, so it's not required exactly in this thing, but we can just assume it as width into height. So it's about 2.9 meters square. So the tires are this R16 215 by 60. Uh, so we get the tire radius as about 0.33 meters. And the powertrain efficiency, I have assumed it as 0.85. So why 0.85? So uh, like motor efficiency, I have assumed it, let us say 0.9, and and zero point 0.9 into, like, let us say transmission efficiency is, like, overall driveline efficiency, I have assumed it as 0.95. So a product of that, it's like roughly 0.85. So that's how I have assumed it as 0.85. So regarding the tire size, so anyone knows how to read the tire size? How do we read this tire spec?
R16 means that 16 is the inner diameter of the tire,
Okay,
and 215 is I think the width of the tire,
okay,
and 60 is I think from the that is the radius of the tire, so inner outer minus inner.
60 is what? Sorry, this 60.
60 is the outer radius of the tire minus the inner radius of the tire.
Uh, okay. Uh, so fine. Actually, it's, so you are right. So about, so 215 is the width of this cross section, and 16 is basically the inner diameter, as you rightly said. So it's in inches. So it's 16 inch, and this is 215 in mm, and this 60 is basically, uh, what is this length as a percent of, as a fraction of what this value is. So in percentage, so this is basically 60% of this width. So it is 60% of 215 of this 215. So it is something, how much? About 120, 130 around that in mm. So to find the outer diameter of the tire, we have to add like this 16 inches. So this into mm we have to convert. So it, like, we have to multiply it by 25.4. So, 16 into 25.4 plus tire outer diameter in mm, and divided by 2 will be the radius. So we get about 0.33 as the radius in meters. So to, to calculate tire sizes, we have, like, online tire size calculators. So for example, this website over here below, tiresize.com. So you can actually get visualization of all the dimensions of the tire. So you can use this website anytime if you have want to, you know, get the tire sizes. Yeah. So coming back to our gearbox design. So if we calculate like using this 1800 as the maximum, the gross weight, and I got the maximum gear ratio as 9.334 using this assumption, and corresponding to 10,000 RPM, I got the minimum gear ratio as 10.43. So the gear ratios are nearly the same, and like the way you got, I also got a maximum gear ratio value of 9.33, which is actually less than what is the minimum ratio. But we can observe that they are nearly the same. So there is nothing wrong in this calculation as such. What it So if we have made an assumption of 10,000 RPM. Now if we just reduce it to, let us say, 9,000 RPM, like, then what will be the minimum ratio that we get? So then we get it about 9.39, so which is actually even closer to this value. So it is possible that our assumption of the maximum motor speed may not be the actual, the correct one. So if we consider a gear ratio that is designed from the gradability point of view and the gear ratio that is required from the maximum speed point of view, they both are actually the same, right? So what does that mean then? So how will we interpret this result?
A single gear is enough for that.
Right, exactly. So we actually are able to fulfill both the gradability requirement as well as the maximum speed requirement just with the same single gear ratio. So that is the advantage of the electric motors, so which you can provide very high torque as well as very high speed using the same motor. So you may not need always this multi-speed transmissions. So I think it is in your case, like probably if you work out with a higher in addition to the curb weight, if you consider a higher gross weight and appropriate tire radius, so then you will also probably get a similar result, right?
Yes, I assumed lesser weight and more efficiency. So
Yeah. So, any doubts up to this point?
yes, sir.
Yes.
So like in the previous slide, you said if we achieve the maximum speed at 9,000, so uh, what factors come into play when we want to achieve a maximum speed at say 9,000 or 10,000? So how do we decide at what RPM are we achieving that speed?
Uh, how do we decide? So there will be so see, generally at max, like very high speed, the torque requirement is going to be quite low. So, then it can be either like so if the if the motor curve goes like this, and let us say for zero grade, this is the tractive force or tractive torque versus vehicle speed kind of thing, curve, and then if this is where it intersects, so then that can be defined as the maximum speed that we can achieve. For design purpose, so if the motor maximum RPM is actually um, even farther, then we can actually limit our operation to this point. Like, this is what we require. But if our curve actually goes something like this, it does not intersect at all. This motor maximum torque available. So at zero grade, this is like, let us say 0% grade on a flat road. This is the curve that we get, let us say, and this is the maximum motor RPM. Now, then in that case, we will let us say assume it to be the maximum speed. We will define it with respect to the maximum motor RPM. So, so in this case, let us say we assume it to be like that. The maximum speed occurs at the maximum motor RPM. Does that answer your question?
Okay, so it basically depends on what type of tires we use. So on the tractive
Yes.
force, it depends.
Yes, yes. Yeah, so if you use a smaller tire, then we may need a lesser gear ratio or something like that. And
Okay, sir. Yeah. Thank you.
yeah, so maybe we can actually try the same for Tata Tigor EV as well. So, so maybe in the next uh, 5 minutes or so, maybe like 5-10 minutes or so, we can probably try this as well. So I have just pulled out the specs for you. So now you can actually now suggest me like what do you think what so we'll do this activity together. Uh, so now the maximum motor torque is about 170 Newton meters, and the maximum speed, let us say we assume it to be 120. I don't know, maybe you can just check online what is the maximum speed of this vehicle. Not sure about this thing. Gradability was given as 29%. So and the tire size was about like this is the thing which I got online. So you can just check and confirm that like in the next maybe 2-3 minutes or so, or 5 minutes, like that what are the specs, and then again we'll try to do the same calculation. Let what is the maximum ratio and minimum ratio. Uh, yeah, and we also need the weight. So yeah, so the curb weight is around 1.35. So let us say we assume like the gross weight to be like for 4 passengers of each of 70 kg on an average. So 280 kgs plus 50 kg of cargo, let us say. So we let us say like it is 1565 kg as our gross weight. Then the rolling resistance coefficient we can actually assume it to be the same 0.01. So what will be the value of alpha for this?
(16.1 degrees).
All right. So yeah, so these are the two equations. So now let us say if we assume the same way, let us say 10,000 RPM as the maximum motor speed. So then what will be the gear ratios now? Let's say we'll assume the same powertrain efficiency of 0.85, maximum motor speed is let us say 10,000 RPM. So what will be the tire radius first of all? Like anyone has calculated the tire radius? So anyone was able to get the gear ratios?
I'm getting the maximum as 8.9 and the minimum as 9.17.
Okay. So yeah, so again you get the nearly the same values, right? So based on gradability criterion and maximum vehicle speed, so it seems that the trend is that uh, for the current, the electric vehicles that we see commercially available. So it seems that we are able to achieve the gradability as well as maximum speed objective with just the single gear ratio. So we may not need a multi-speed transmission for that, right? Agreed. Everyone agrees.
Yes, sir.
Okay. I hope this exercise was helpful to understand these things.
Yes, sir.
Sure. So now then next we will again so I think we had enough of theory, so we'll just I thought like we'll probably try to have some interesting um, comparison between some of these current to look at the current trends in the commercially available electric vehicles. So one interesting comparison which I found is between these two vehicles. So can anyone recognize which are these two vehicles? Anyone know is able to recognize these? Or at least like if you can I think you can recognize the brand at least I think.
The bottom right one looks like a Porsche Taycan EV. I'm not sure.
Right, right, you are right.
And the Tesla model maybe S.
Yes, yes, you are right. So this is Tesla Model S and Porsche Taycan. That is right, so you are right. uh, so these are very interesting, like these are currently popular very high performance electric vehicles, and they are quite close competitors, like considering their the performance that we get. So it's an interesting comparison to look at, and also an interesting trend in terms of the transmission point of view. It is also interesting, and the overall powertrain design aspects. So it's an interesting comparison to look at. So I will try to get to know about these vehicles. So so if we like do just a top level comparison of the basic specifications. So Tesla Model S has, like it was launched in around 2012 I think, so around 2012, so it has been around for more than 8 years or something. And Porsche Taycan was I think launched around 2019 or so, or 2018 or 2019 I suppose. And then they came up again with various models. So Tesla Model S has launched like different variants depending on the size of the battery pack and the different performance. So like they had models which favor the range, like they have more mileage, and some models which give like better, like more performance as compared to, and they like there is a bit of a compromise between, like what, whether we favor the acceleration performance range. So they had different models. So the current top end model is what is called as the Tesla Model S Plaid, PLAID. Uh, and there was kind of this model was kind of launched recently, and probably in response to this Porsche Taycan. And like they had like they different like they keep on upgrading their uh, motor software. So the great thing about Tesla is that whatever software updates they can actually upload it onto they can update it over the air. So like the way we get apps like updates to the apps, uh, like the way that way they actually can update their software. And then so the software but basically what it does is that it's like traction control. So it determines how much power to extract from the motor at a certain point of time depending on the driver inputs and road conditions and all these things. So this played variant, it's like ultra high performance. It has like peak power of about 100 and like 1020 HP. It's about 750 kilowatt. And whereas the normal Tesla Model S variant is about 670 HP or 493 kilowatt. Uh, and whereas the Porsche, so Porsche has actually again come up with different models depending on like what is the requirement. So they have a 4S model, Turbo and Turbo S, and like depending on like if the Turbo S is like the one which has the highest performance. Uh, Whereas there are other models which have like better range and probably lesser performance. So, so this played upgrade with that, they were actually able to achieve 0 to 60 miles per hour acceleration in just 1.99 seconds. So that's super quick. And the other like the regular Tesla Model S variant, like it's about 3.1 seconds to accelerate from 0 to 60 miles per hour. So 60 miles per hour is roughly close to 100 kilometers per hour. So it's about 1.6 times uh, miles per hour. So it's about um, roughly about 100 kilometers per hour. So the Porsche Taycan, it is able to achieve like 0 to 100 kilometers per hour acceleration in about 2.8 seconds. So it has a launch control mode like this. So it can uh, so in these vehicles, they can actually lower their suspension, they can lower down their chassis, uh, so that uh, for better aerodynamics, they can actually lower down their suspension. So similarly in this Tesla Model S, they have that feature. And with this launch control, they can achieve this overboost, that's so additional power boost. So for a like maybe 2 3 seconds or so, it can actually deliver its peak power. Uh, so that's like the peak power is available only for a short duration because then the motor gets heated up. So this is like a top level comparison. So anyone knows what is unique to these, or anyone is aware of what are the latest trends with respect to these two models? Anyone wants to contribute anything on that? Anyone is aware about these? Like, what is the unique thing about these two?
I'm
So
not sure
basically,
if
you get,
it's
yeah,
positive or negative, but the Tesla Model S played as a weird steering wheel.
weird steering wheel. Okay, okay. So recently, this like this has a, you are aware of cheetah stance upgrade.
Yes, sir.
Yeah. So you do you know what it is? What it does?
Sir, it drops the ride height and suspension setups change, something like that.
Yes, you are right. So it actually why it is called as cheetah stance is that, so when the cheetah is about to accelerate, like when it wants to run like perform a sprint, so then it will actually lower down its front legs, like it will consider this as cheetah. So it will actually lower down its front legs when it is actually trying to make a sprint. So then this its torso is like in this kind of fashion. So similarly, the Tesla Model S has this thing. So it in order just lowering down suspension. In addition to that, it can actually lower down the front part of the body itself. So then in that cheetah stance, so while launching, it can actually do this kind of a maneuver, and then with that, it can launch it with an exceptional acceleration, and then it's able to achieve this. So this mode actually gets some time, needs some time to get activated, but uh, once that is activated, it's actually able to perform 0 to 60 miles per hour in 1.99 seconds. So this actually comes with asterisks. There are several conditions need to be met for this thing. So conditions like what is the road condition. So it needs specially prepared high traction kind of road surfaces, and on this it can achieve this thing. If like with non-prepared kind of surfaces, it will probably go something over to 2 seconds, so maybe 2.1 seconds up to that. But still, it's like very high, ultra high acceleration performance that can be achieved with this Tesla Model S. What about uh, Porsche Taycan? Like anything specific or anything unique to this particular vehicle? Anyone is aware? So Porsche Taycan is like it's the first production vehicle which has a multi-speed transmission, like multi-speed transmission-based electric vehicle. So that's the unique thing about this. So, so why we are actually trying to compare these two is like they have, the acceleration performance is very close. So what about the Tesla Model S? What about the transmission or whatever? Anyone is aware about the powertrain and all aspects of this?
It has a single speed transmission with a gear ratio of about 9.
Yeah, right, right. So Tesla Model S is like more or less of a single speed, uh, gear transmission. So whereas Porsche Taycan has a two-speed transmission. But so it's actually interesting to see how they get comparable performance, um, even though their powertrains are somewhat different. So there are some features which are common, some features which are actually quite different. So we'll see that thing. So the current Tesla Model S powertrain is such that it actually uses dual motors. So it uses one motor on the front axle and another motor on the rear axle. So the first, like the front wheel, like motor is coupled with some transmission, which is again a single speed, about 9 ratio as like. So I think Akash said, Akash right. So um,
Yes, sir.
yeah, so it has like that gear ratio of about 9, and that is coupled, like the transmission is output is coupled to a differential. On the rear side, we again have a similar motor which is more powerful than the front one, And we have another single speed reduction, and that is again also coupled to a transmission. So in the recent uh, the model played model, so they have a tri-motor kind of configuration. So where they have actually used three motors. Uh, so on the rear axle we have two different motors. So then they have actually eliminated the differential on the rear wheel side. So then that uh, needs different controls, and the control aspects are quite challenging. So then to achieve the function of a differential, we need to provide be able to control the motor speeds accurately, so that while turning the appropriate difference is maintained between the vehicles, the wheel speeds on the inner side and the outer side. So then so that the vehicle does not skid. So that is about the Tesla Model S. Similarly, uh, for the Porsche Taycan, we also have a similar kind of a powertrain where they use different motors, a smaller motor on the front axle, and another bigger motor or more powerful motor on the rear side. So the rear motor is about 449 HP in the Porsche Taycan, and it provides a torque about 550 Newton meter. And the interesting part is that it has a two-speed gearbox on the rear side. So the motor output is connected to the two-speed gearbox, and the output of the two-speed gearbox is connected to the differential. So it has two gear ratios. So first gear ratio is about 16 is to 1, and the second gear ratio is about 8 is to 1. So it's interesting to see how they have designed this transmission. So we'll go through that in some detail. So as I said, like on the front axle, we have a coaxially mounted transmission. So uh, they use a single speed planetary gear, which has an overall gear ratio of about 8 is to 1. And the motor and transmission are mounted coaxially. And the transmission output is connected to the differential on the front axle. On the rear axle, uh, there is a two-speed transmission. So the first gear is meant for mainly from additional acceleration from starting, whereas the second gear is it largely ensures that the motor operates in its efficient zone, and it provides adequate power at very high speeds. So another feature that this vehicle has, that it can actually decouple the rear transmission. It can completely run it as a front wheel drive, and just disengage the rear wheel transmission so as to reduce losses. So in these vehicles, both in the Tesla Model S as well as Porsche Taycan, we can actually send different power requests to front. So we can actually decide how much power to draw from the uh, front motor, and also how much power should be supplied by the rear motor. And so like together they can actually provide very high power, and that's how actually they achieve a lot of uh, fast acceleration and all that. Any doubts? Yeah, so this is a photograph of the rear axle of the Porsche Taycan. So, we can see how so they are using permanent magnet synchronous motors. And anyone is aware what kind of motor do they use in Tesla Model S? Anyone knows what kind of a motor do they use in Tesla Model S?
AC induction motor.
Sorry,
AC induction.
AC induction motors, right? Right. So what is the advantage of using AC induction motors? Anyone is aware of that?
It's pro than PMSM.
Sorry, I'm sorry.
It's more robust than PMSM motor.
Okay, robust in what sense?
As in there are less moving parts because it's an induction motor, so there is a rotating magnetic field involved.
Yeah. Yeah, rotating magnetic field will also be there in PMSM. So it's like basically the difference in how do they achieve that. So so the induction motors will have like windings on both stator as well as rotor. So whereas this has permanent magnets installed in the uh, this thing stator. So this like PMSM is actually uh, better suited. Like it has better thermal control is better like as compared to the induction motor. So because the rotor is inside and it has like huge current passing through it, then it's when it gets heated up, it's difficult to cool that thing. So thermal management is more challenging. Whereas PMSM, it's like less of a challenge. But it, on the other hand, it actually uses costly, very expensive rare earth magnets. So that's a downside of that. But the later, I think Tesla Model X or something, I think they use PMSM here in the latest, one of the latest models of the Tesla. Anyway, so this is another view of the rear axle of the Porsche Taycan. So we can see that some part of cut section of the transmission is visible. So so the differential is integrated to the transmission and its whole unit is like quite compact. It is mounted on which is mounted on the rear axle. So this is the exploded view of the two-speed transmission. So so this is the part which has the planetary gear, and these are the uh, spur gear or helical gear stages. Um, so in that, like they provide like with this whole transmission, they are able to provide two gear ratios, 16:1 and 8:1. So we'll see the parts of this transmission. So this is the view of the planetary gear set. So so these are like the planet gears which are shown over here, and so the and the sun gear is over here, shown over here, and this is the planet carrier which is shown over here. So they have inner planet as well as outer planet, like two different sets, and with this planetary gear, so they are actually able to achieve a very high reduction ratio. So what is the advantage of planetary gears? Anyone is aware of that? So planetary gears are actually very compact, and they can provide like very high speed reduction within a small space. So Yeah, and then they have a shift actuator which decide like to engage or disengage the planetary gear transmission, and the dog clutch basically engages or disengages the planetary gear stage. Then they have a spur gear, so-called spur gear stage, which is basically like the conventional, with the way we have a conventional gearbox with uh, sets of helical gears, and they have an electronically controlled limited slip differential, which is and the transmission output is connected to the differential in this way. So, so the two-speed transmission of the Porsche Taycan, it has three shafts. So it has basically two spur gear stages, like the main shaft and counter shaft and the output shaft. So three shafts, and they use a shiftable planetary gear as we discussed. So for the first gear, which provides a ratio of 16:1. So the first gear is mainly used in the sports mode or sports plus mode. So there are different modes of driving. So they have like normal mode, sports mode, or range mode as well. And with launch control is also available in this mode. So this transmission works like in such a way that like uh, so when it's in the sports mode, so then the transmission uses the first gear for a longer time, and then it shifts to the second gear with a overboost. So the second ratio is around 8:1, and it is similar to the or more or less same to the motor plus transmission on the front axle. So with this, the vehicle is able to achieve about 260 kilometers per hour of top speed. So this two-speed transmission has like single actuator for engaging different gears like the first gear, second gear, or neutral, reverse, and park, these modes. So this shift actuator, it has like actuates like two levers. Uh, so this like two levers. So it uh, kind of pushes or pulls the dog clutch as and when required. And it has a multi-plate clutch. So we saw that on the planetary gear, this ring gear. So they have a multi-plate clutch which uh, we can engage or disengage. So if this multi-plate clutch is open, then the planetary gear can run as the usual way where the power flows from sun gear to the planet gears and then through the ring gear and then eventually to the planet carriers. If the multiple plate clutch is engaged, then the transmission is that the planetary gear, like the relative motion between the planet gears is locked. Then the whole planet gear then rotates as a single unit. The then that actually provides just a 1:1 ratio. Then there is no speed reduction in that case. So this is how they get. So the planetary gear basically provides two ratios. One is this the ratio when it runs like with the planetary gears free to rotate, and the other one when it is blocked, it provides a ratio of 1:1. So the planet gear ratio is 2:1 when it is like when the multi-plate clutch is open, and when the multi-plate clutch is engaged, then then the gear ratio of the planetary becomes 1:1, and then we engage like the second gear, and then that becomes a ratio of 8:1. So like when we shift to the second gear, then this dock clutch is opened, so that will actually disengage the uh, planetary gear stage, and then the shift actuator like uh, will disengage the dock clutch, and then the multiplate clutch is also closed, and that's how we get the second gear ratio. So this, by blocking the planetary gear, the gear losses are because of the rotating components, they are actually reduced, and then we get increased efficiency in the second gear ratio. So any doubts till this point? Now on the front axle, we again have a motor along with a coaxially mounted transmission. So that front axle has a single speed transmission engaged along with the motor, along with its inverter. So there are two. So this this output of the transmission is connected to the differential, uh, again coaxially, and then the motor is mounted directly on the front axle itself. So then there are the axle shafts actually go through the motor's rotor axis. So it's uh, so this front axle transmission, it actually uses two planetary gear stages, and you can see that it's like quite compact an arrangement. So this transmission directly is connected to the motor. It's mounted coaxially, and the motor is actually directly mounted on the front axle, like on the center line of that axle. So it's between the front wheels, and one of the axle shaft, it actually passes through the center of the motor. So the rotor is actually hollow, and the axle shaft actually goes through the motor uh, center line. So that's how they actually achieve the front axle design. Then there is extensive amount of regenerative braking that this vehicle can perform. Also, like they have different options, like whether to use the front motor to provide regenerative braking. So in this regenerative braking mode, the motor will be used as a generator, and that will absorb energy. So instead of applying friction brakes, so the motor will work as a generator and absorb the kinetic energy of the vehicle and send back the energy, like so that energy is used to charge the battery. So it can recover some of the kinetic energy which would otherwise be wasted in friction brakes. So it as heat and sound, etc. So then uh, the regenerative braking is available up to a level of 265 kilowatt and up to a maximum deceleration of 0.39 g. Basically acceleration due to gravity. So that's about the regenerative braking part. So up to this point, anyone has any questions?
No,
So
sir.
yeah, sorry. So we saw that this interesting trend, like how so with two different motors, along with two different single speed uh, like single speed gear ratios, we can, like indirectly we are using two gear ratios. So and we can manipulate how much power that we, the front axle motor to be provide. So generally when the vehicle is operating on highways or so, then we can use the front motor, and that does not like highway cruising may not require that much of a power. So then the front motor may be sufficient for that, but for accelerating, then the rear motor can be used. So there are different combinations that the powertrain design provides. And interestingly, with the Porsche Taycan, they have actually designed a two-speed transmission along with a single motor uh, connected on the rear axle. So that's an interesting comparison that we saw. Now we saw this like how we design like different gear ratios and different transmissions. So now we'll see how gear shifting happens, like on what basis. So, so if we see that uh, like in a conventional vehicle, let us say this is a BSXT map. So generally in the gear shifting logic, in the control logic, let us say if we have an AMT or anything, even for a manual transmission, so we have upshift and downshift lines. Basically, they represent the points along, like they create an envelope in which we want to confine the engine or motor operating point. So the upshift line is something which decides, uh, let us say, when to shift into the next higher gear, and the downshift line is the criteria which decides when to shift from the current gear to the next lower gear. So, so based on the driver accelerator pedal or brake pedal input, we can translate it into a torque requirement. So this upshift and downshift line basically say decides that for a certain torque versus speed operating point, like let us say it's in some nth gear, then and the vehicle is, let us say, accelerating. So let us say if the vehicle is accelerating and then the engine speed goes, somewhat like outside this upshift line, then if the engine operating point is outside that, so let us say if, like let us say instead of this, if the engine operating point was somewhere here, where the engine has now reached its speed limit, it has crossed the upshift line, so it is providing this much of some torque, and the engine is running at this speed corresponding to this point. So now it has crossed the upshift line. So what the gearbox, like there will be a shift command that will be generated, because the upshift point corresponding to this speed is here. The upshift at the top, this point is like this way. So then there will be a shift command that will be generated, and it will ask the gearbox to shift in the next higher gear. So then what will happen? The engine speed will get lowered, and it will provide like higher torque somewhere. So the operating point may be shifted somewhere here. So probably in the better efficiency zone. So the upshift points are placed such that it tries to uh, confine the IC engine operating point or motor operating point in the better efficiency zone. So similarly, if if we kind of reach, let us say, if we are operating in a second gear and we suddenly encounter a steep slope, then it will demand much higher torque at a lower speed. So then uh, So if we compare it with the downshift point, it is higher than the corresponding the torque required is higher than the corresponding torque at along the downshift line. So then there is a downshift command, so that is generated. So because the engine cannot supply this much of torque at this speed, so because the downshift line has kind of prevented the engine in operating in this area, so then it will ask the transmission to shift into the next lower gear. So let us say then it will shift from second gear to the first gear, so that with the higher gear ratio, it will operate at a lower torque and higher speed. So then again, it may actually come somewhere here or something like with the next lower gear engage. So then the engine will run at a higher speed and lower torque. That is how the engine operating point is manipulated by gear shifting by using upshift and downshift points. So any doubt on this part? So these upshift and downshift lines are something which are programmed into the transmission controller. Like in terms, like if we consider an AMT, this will be some logic which will be programmed inside the controller, and then based on the driver's accelerator and brake pedal input and clutch pedal input, it will send appropriate shift commands by comparing the required engine operating point with the upshift or downshift line as and when required. So, any doubts on that? So now, since we looked at uh, the Porsche two-speed transmission, we saw how they designed the transmission to achieve two gear ratios using planetary gears and all. Now we'll also see how they have constructed the gear shifting strategy. So this graph shows the wheel torque that we get versus vehicle speed for different gears, like the on the front axle. So the front axle is a single speed, so the red curve shows the wheel torque versus vehicle speed, what we get from the front axle. And for the rear axle, we have two different sets of like two different green motor curves. So one is for the first gear. So the motor has a maximum RPM of about 16,000. So corresponding to 16,000 RPM, it's like able to achieve a vehicle speed of maximum of about 200 kilometers per hour in the first gear. And with the rear axle ratio, like rear, so in the second gear of the on the rear axle, it's able to achieve speed up to 260 kilometers per hour maximum. So then here, if we look at these two green curves, so there is a certain region where these two curves kind of overlap. So then there is no gap here that we can see. So here this is the zone where they generally keep the gear shifting point. So at typically at in when the vehicle is running in this speed range, they will generally shift the transmission to the from the first gear to second gear or second to first or whatever as required, so as to have smooth shifting. So then there is like if it was shifted somewhere here, then there is a gap. What is the torque that is available with the second gear in this at this speed and in the first gear at this speed. So here both coincide. So then we can smoothly shift from first gear to second gear without any gap or any interruption in the torque. The driver will not feel any interruption in while gear shifting. Because of this, if we shift it over here, then the dark blue curve is the combined wheel torque that we get with both of the motors combined together. So in the Porsche Taycan, the uh, gear shifting happens automatically. Automatically, there is no driver does not have control over the shifting. So the shift logic is programmed for different modes. So they have different modes like range, sport, or normal mode. So in the range and normal mode, they generally prioritize the second gear. So the second gear is used more because it's like for normal operation or the normal kind of speeds, then and the kind of performance that is expected during normal driving. So the second gear is able to provide that. And if the driver presses the accelerator pedal very hard, like, depending on the rate at which accelerator pedal input is provided, that is also taken as an input along with the absolute accelerator pedal input. So with that, they actually activate the first gear as and when required. So in the range mode, they also have the first gear which is needed like in the reverse gear. Other than that, they generally prefer the use of the second gear itself. So here the gear shifting logic is represented as like uh, the blue curve for upshift and purple curve for downshift. So we see that the downshift curve is above the maximum wheel torque that is available. So it won't generally shift into the downshift from second gear to the first gear mostly until there is an extreme accelerator pedal input. So this is translated as the driver torque request. So the purple curve uh, shows the driver torque, like, or basically the upshift and downshift curves are representation of the driver's torque request versus at a certain vehicle speed. So similarly for the sports mode, we will so if we compare between range mode and sports mode, the blue curve is shifted rightwards as compared to the range mode. So the upshift point from first gear to the second gear is delayed kind of. So the first gear is available for a greater amount of time in the sports mode, and then it can shift into the second gear. So, so that's how we get greater acceleration using the first gear and then shift to the second gear for higher speeds. So similarly for downshifting, like when there is high performance required, so whenever it needs to climb a steep slope or something, then it can actually shift down to the next lower gear to get uh, to shift into the second from second to the first gear to provide very high torque. So any questions on this? So another example which I just pulled out is so ZF is another company which is a leading transmission manufacturing company. So they launched a two-speed transmission for electric vehicles. So they launched an entire electric drive, like so a motor plus transmission combination. So this concept is meant for passenger vehicles currently, and then they can actually, what the company claims is that they can actually scale up this whole concept for high performance vehicles or commercial vehicles or and so on. So currently they have an electric motor which is designed to pair along with this uh, two-speed transmission, which has a rated power of 140 kilowatt. And what the company claims is that with this two-speed transmission, there can be uh, it can actually gain mileage or up to 5%. So it can travel 5% more distance in the same amount of charge if they use a two-speed transmission in comparison to a single-speed transmission. And they have designed this to shift gears from first to second to about 70 kilometers per hour. So that is another concept that this company has proposed. So similarly, there are Bosch has also a continuously variable transmission that is they have launched for electric vehicles, and Eaton is another uh, transmission manufacturing company which I was working for earlier. So they have two-speed as well as four-speed transmissions for electric vehicles. So generally for passenger cars, the trend has been like 99% of the vehicles they generally use a single speed transmission. There are few examples of like in addition to the Porsche Taycan that we saw, Audi e-tron is another vehicle which uses a two-speed transmission. So apparently Porsche Taycan and Audi e-tron, they have the same chassis and they share the same chassis platform, and about 40% of the components are common. So it is likely that the transmission is also probably the same. Uh, so again, that's another electric vehicle which uses a multi-speed transmission. And there are like Formula E race cars which also use multi-speed transmissions. But generally, the trend for commercially available electric cars has been like largely with the use of single speed transmission. So, so that's all with the content that I had for today's session. So I think this will be the last session available from my side. So maybe, sir, hello, sir, are you there online? Hello, Abhishek, sir, is there?
I think he's not there in the meeting.
Okay. Sure. So I think this was it that I had to cover for today. So any questions or any comments, any feedback from your side? So probably this will be the last session from my side. Uh, how did you find the session? Any feedback? Any comments? So any feedback or any comments that you have to share?
Yes, sir. Your sessions were really informative, and I especially like today's lecture because it had all the different systems which are currently in use. So yeah, I
Yeah,
found it quite interesting.
sure. Thanks. So is there anything more that you would like to see? So because currently the thing is that so your semester is getting over your classes are getting over in the next week, right?
Yes, sir.
Yeah, actually, I wanted to show you demo, like simulation demo kind of thing, but right now in this week, I am kind of occupied, so I may not be able to take another session. But later on, if you are interested, I can actually try to show you demo later on. All of you can just connect for an hour or so, then we can actually have a small demo if you are interested later on. Not for the exam or anything kind of thing, but just for knowing and if you are interested, I can think of that.
Sure, sir.
Okay, okay, fine. So if you can like so how will be your availability, all of you, are you available in the next week towards the end or something like that, towards the end of the next week or so? I think Good Friday will be having a holiday or something like that, I think. 15th April. So when is the
Yes,
last
sir.
date for sorry? Yeah,
On 8th, 9th, 10th, I think we'll be occupied. So
8, 9, 10th will be
next
occupied. Okay.
weekend is not possible, I think.
Okay, fine. Uh, okay, fine. So I will actually coordinate with Abhishek sir and let you know. Uh,
Yes, sir.
so, so if you can, someone, if you can, if I can actually share my contact details as well. If you want, so we can, if anyone is, wants to know more about anything else, so I can just share my contact details. So you can contact me on this number. So this is WhatsApp as well as phone, and uh, this is my email address. So you can email me or contact me on phone anytime if you want to know anything, or you are interested in this topic. If you want to work on a project or something, you can. If you want to visit IIT Bombay, if you need anything, you can always contact me. Uh, so I will coordinate
Yes,
with
sir.
Professor Abhishek and let you know about if we can have a demo or so later on. So So it was nice interacting with all of you. I hope you enjoyed and learned this new topic of electric vehicle transmissions.
So, will it be
Yes,
possible for you to share these slides so that we can refer back to them later?
yeah, I will check that. So I have to, yeah, I can share some of the slides. Yeah, that I will let you know. I will pass them on to Professor Abhishek and then maybe he can share them with you later on.
Okay, sir. Thank you.
I think that should be possible. Okay, anything else? So all of you are third year BTech students or MTech students or what is the general
Fourth year
class?
BTech students.
Fourth year,
Yes, sir.
fourth year BTech student. Okay. Good. It was nice interacting with all of you. And so you can always contact me if you want to know anything.
Yes, sir.
Is there any topic that you want, like if in that demo session, if we have, then like if you want something like to be covered or something, maybe I can try that. Is there anything specific that you want to know more? So if not, I think then we can actually close the session. So I will coordinate with Professor Abhishek and let you know about like the demo session if we are able to have that. So thanks all of you. So all
Thank you,
the
sir.
best. Yeah,
Thank you,
thanks.
sir.
All the best. Yeah.